Okay. Welcome back to EE210B. We'll continue our discussions of stochastic gradient algorithms. Last time I introduced what stochastic gradient algorithms are, and we established their convergence, right, by showing that the second order moment and the fourth order moment of the weight arrow vector are bounded, right? And I told you the size of the region that they converge to. Okay. Now, what we would like to do today is the following. I don't want only to know that the mean square error converges to a bounded region. I would like to be more explicit and tell you exactly what the size of that region is, right? What the mean square error performance is. This is something that we will do in the next lecture, okay, not today. Today I'm going to prepare for that lecture. It turns out that in order to assess the performance of stochastic gradient algorithms, it becomes very useful and very helpful to introduce a long-term model for the evolution of the dynamics of the algorithm. So today I'm going to motivate this model, and then you are going to appreciate why this model is useful for studying the performance of learning and adaptive algorithms more in the next lecture, okay? So let's start. Okay, so this material is based on chapter 4, okay, the early part of chapter 4, and the next lecture will be based on the later part of chapter 4. Okay, so if you remember last time we considered stochastic gradient algorithms, right? So they were algorithms that looked like this. The new weight is the old weight minus a step size times an approximate gradient vector evaluated at the current estimate, right? This is the gradient relative to W transpose, and we use an approximation for it. And we studied two situations, one with mu constant and one with a mu that decayed down to 0, for example, of the form sum tau over I plus 1, right? We studied the convergence of two algorithms, constant adaptation or learning and a decaying step size situation. Now, we showed in the second case when the step size decays to 0, for example, for step sizes of this form, we showed that the estimate will converge. Even though you are using stochastic gradients, the estimates will converge to the minimum of your function, right, of your risk function, which is the desirable result. However, the convergence rate will be at the rate of 1 over I, so it decays at that rate. Okay, so this was one conclusion we established last time. In comparison, if the step size is a constant, some constant value mu, we showed that there is an upper bound on mu, meaning that for small enough mu, the algorithm will converge, will be stable in the mean square error sense, converging in the following sense. It doesn't mean that Wi goes to Wo, right? We cannot guarantee this anymore. It doesn't converge pointwise to Wo because of the effect of gradient noise. Instead, in the constant step size case, what we showed is that the second order moment of the weight arrow vector, or let's just refer to it as the arrow variance, right, converges to a region whose size is of the order of mu. So if your step size is very small, you will perform relatively well, right? So one interpretation, again, for this result is that if this is the solution here, right, if this is the optimum, and if you draw a circle, right, and if this distance measures the norm of the error squared, right, then what this is essentially saying is that on average, right, on average, this norm squared will be within a circle of radius mu, right? That's intuitively what this result is saying. So we were able to show that while you do not converge exactly to W0, you converge close enough in the sense that the mean square error is of the order of mu. And more importantly, we show that this convergence occurs at an exponential rate, alpha to the I, for some number alpha that's strictly less than 1. So this is faster convergence, much faster than 1 over I. So what you get here is that even though the mean square error which is this quantity here, over time is converging to within some area, right, of size or mu, some region of size or mu, that convergence rate here is exponential, is fast. So if the size of the error that you get in steady state is good enough for you, is small enough, and good enough for your application, you don't need it to be zero. In many applications, you don't need it to be zero. If the size of that error is good enough for you, then using a constant step size is advantageous because you will converge to that level very fast, much faster than converging to zero with a decaying step size. So that's one element of this comparison. The second element is a constant step size maintains the adaptation ability of the algorithm and the learning ability of your algorithm, right? If W0 changes, a constant step size algorithm will be able to track that change, right? Because you are computing the approximate gradient vector from streaming data, from data that's coming in and being influenced by the changing dynamics, right? The drifting vector. You understand these points before we move on? Very good. Okay? So the convergence is geometric. I already mentioned it. But now, I'm not only interested in knowing that I'm converging to a region of this size, I'm interested in knowing, because what this notation means is that the lim sup is bounded by some multiple of mu, but I haven't told you the size of that constant, right? It can be very large, it can be small. It would help for us to know more precisely what the right-hand side expression is. Okay, the right-hand side expression here for mu very small, it can be any polynomial expression involving mu squared, and higher order powers of mu, right? When mu is very small, the first term, which is of the order of mu, dominates, and therefore we write it as O of mu. It would help for me to know more precisely what this value is. And because that value will reflect the performance of the algorithm, will tell me more precisely the size of the error, right, of the mean square error in steady state. Okay. The answer to this question will be pursued in the next lecture. In the next lecture, I'm going to evaluate the first order term, the term that's linear in mu, and tell you exactly what that expression is. And that performance expression is useful. Once you derive it for different algorithms, you will be able to compare not just the convergence rate, but what mean square error you can expect of the algorithms in steady state, okay? But that's the theme of next lecture, okay? In this lecture, I'm going to motivate a long-term model, okay, that will help me reach this objective. Okay, if I try to assess the performance of the algorithm by working directly with the current form of the algorithm, some difficulties will come up, which I'm going to explain to you what they are. Okay, and for this reason, I spent this lecture introducing this long-term model, and we will do the same thing later for networks, and you'll appreciate the convenience of this once you see the model. Okay. So that's what we are going to do today, okay? Before I get there, very often I'm going to use this language, okay? From time to time, I will be saying we are operating in a steady state regime, or we are operating in a slow adaptation regime, okay? So what the language means, steady state means I let time flow to infinity, right? Slow adaptation means I let the step size be very small, so you're adapting very slowly, right? So if I use this terminology, what it really is referring to is to these two facts. Either mu is very, very small going to zero, or I is very, very large going to infinity, right? This is just terminology, okay? Very good. So what I'm doing today, I will come up with a long-term model that approximates well the behavior of the algorithm in steady state. So after the algorithm has evolved for a long time, I'm going to come up with a long-term model that tells me, approximates very well how the algorithm is performing in steady state. Okay, so I'm focused. Okay. And of course, I will also need the small step size assumption. By the way, most of the analysis we do in this course need to assume that the step size is sufficiently small so that stability is ensured. Right? So you saw bounds on step sizes so far, right? So it's not unusual for us to assume that the step size needs to be small, okay? Very good. So let me remind you again of our problem. I have a cost function which is strongly convex and I would like to minimize it, right? And we assume that the Hessian is bounded from below and from above. The bound from below is because we assume the function is strongly convex. The bound from above is because we assume that the gradient of the function is Lipschitz. Remember, that's where these conditions come from, okay? So I always, okay, and this assumption is just stated what I told you, and here I'm spelling it out. The function is twice differentiable, okay, strongly convex, that explains the bound from below. The gradient is Lipschitz, that explains the bound from above. Okay, so these are the standard conditions. I'm just reminding you of these conditions. I already explained many times that they are satisfied by many cases of interest. And then this is the stochastic gradient algorithm that we introduced in the last lecture, and we studied it in some detail and showed that the error vector has bounded second order moment and fourth order moment under certain conditions on the gradient noise. Remember? This is the gradient algorithm, stochastic gradient algorithm, and this is the associated gradient noise. Whenever you replace the true gradient by the approximate gradient, you introduce gradient noise, right? And that noise interferes with the operation of the algorithm. And we showed last time, under some conditions on the gradient noise process, for example, this is one set of conditions I introduced last time, and I showed you that they are satisfied in cases of interest, right? That the gradient noise process is conditioned on the past data, that it has zero mean and bounded variance, second order moment, right? I explained to you last time that we can write, these conditions imply the conditions that you have down here, which are more convenient for our analysis, right? That the gradient noise is conditionally zero mean, and that the second order moment of the noise is assumed to be bounded by the sum of two terms. One of them is a constant, and the other depends on the error vector. Fine? Okay, so under conditions like this, we showed, right, we showed that the algorithm was stable. Okay? Right, we showed the bound I showed you earlier, that the lim sup, right, the lim sup as I goes to infinity of the second order moment of the error vector is of the order of mu, right? And if you remember later in the last lecture, I bounded instead the fourth moment. Remember, I bounded instead the fourth moment, and I think it was 4 here also, and of course for different beta and sigmas. And under that bound on the fourth moment of the gradient noise, I was able to show that the fourth moment of the weight error vector converged to a region of that size, right? I'm just reminding you of these expressions, okay? Yes?
Will the long-term theory be able to give us a stronger bound on norm of W squared than this?
Right. I started the lecture by explaining that's the objective, right? The objective is to be clearer about the O of mu term, to characterize it and give you a more accurate expression for that term. So yes, it will help us, but you will not see that in this lecture. You will see it in the next lecture, okay? You understand it? Okay. Now, so to get there, I need to introduce two more smoothness conditions, which I'm going to explain to you. And again, I'm going to show that these conditions are satisfied in cases of interest. They are also satisfied in other cases, but at least for quadratic costs, for logistic costs, okay, the examples that we have been using, they are satisfied. First of all, S is a gradient vector, right? It's a vector, so it has, and it's random because it depends on the weight vectors. So it has a covariance matrix. So I'm defining here SS transpose. This is the covariance matrix, okay? But this is the conditional covariance matrix, conditioned on the past, fine? So this is actually a random matrix, because when you condition on the past, W is treated as a constant, it remains here. So technically this is a random matrix, but that's the conditional covariance matrix, okay? This is definition, just definition, okay? So far we have been working with the trace of this. When I write this conditioned on F, right? That's the trace of that, right? Okay, the trace of the covariance matrix. Now, in the particular case, when I replace omega by omega 0, right? Your RS becomes RSI evaluated at omega 0. Fine, the covariance at omega 0. And I explained to you in the last lecture that even if the algorithm were to converge to omega 0, you will still have some gradient noise, right? So it still will have some covariance. Okay, now, so this is just definition for now, right? Definition. Okay, now this is assumption, but I'll show you that it's satisfied, at least in cases of interest. Okay. That if you take the limit as I goes to infinity, so in steady state, that covariance, this covariance, which I just defined on the previous page, right, on the previous slide, at omega 0, it goes to a constant value. It's okay that in steady state, the limit of this approaches a constant value. I'm going to show you examples, okay? And I call that constant value R sub S. So this is a very critical quantity. It's called the gradient noise covariance. It's a constant value. It will play a role very much related to the Hessian matrix of your cost function. These two things, the Hessian matrix of your cost function and this covariance of the gradient noise, they will turn out to ultimately determine the performance of your algorithm, as you are going to see in the next lecture, not today, okay? So you are going to see this matrix again next time. This RS and the covariance and the Hessian matrix H evaluated at omega 0, both of these quantities determine the performance of your algorithm. You will see this next time. Okay, so let's see some examples so that you understand these definitions. Let's go back to the mean square error case. Okay, so I have a sequence of data d of I, zero mean. All data are assumed to be zero mean. That's the variance of d. U is a sequence of regression vectors assumed to be row vectors. This is just convention. You can assume them to be column vectors, right? But this is our convention. Okay, so the covariance matrix of RU is assumed to be positive definite. By the way, I assume the regression vectors, these are the only vectors I assume to be row vectors, the regression vectors, okay? This way, this inner product, for example, becomes easier to write it like this. And there are other reasons why I prefer this notation for the regression vectors. And if you took 210A with me, I explained these reasons for you, right? But there is no reason to go through that here. The covariance matrix of U, and this is the cross-correlation vector between D and U. And this is the model. Fine? Okay. Now, I would like to estimate omega 0. I explained to you last time that a good way to do that is to solve the mean square error estimation problem that gives you exactly omega 0, right? I explained this to you last time. However, I cannot run a gradient descent on this because I don't have the statistics. I don't have RDU and RU. Right? I don't have the distribution of the data to be able to find what J is and compute its exact gradient vector. So you run a stochastic gradient algorithm, right? You use the data to estimate your gradient vector. I'm just reminding you of things we did. And if you follow this argument, you arrive at the LMS algorithm here, right? Okay, so this is the approximate gradient, and the true gradient vector would have been instead 2 RU W minus RDU. Fine? If I now subtract this from that, I get the gradient noise, right? This is what we also did last time. I subtracted them, and you arrive at this expression for the gradient noise, right? Now, what would be the gradient noise at 0? Assuming that you converge to the true solution, this term will disappear. So you will just get 2 U transpose V, right? So what is the covariance of this quantity, which I defined as conditioned on F I minus 1? In this case, you don't need to condition it because it doesn't depend on previous W's, right? Okay, so whether you condition or not, in this case, it doesn't make a difference. So let's just remove it. Okay, we don't need it in this case. Okay, so I define this to be Rs of I, remember? Okay, at omega 0. What do you get in this case? You get 4 sigma V squared RU, correct? So the limit, this is already a constant, independent of I. So the limit is itself. So there it is, right? So in the quadratic case, the condition that this RS, the limit of the noise covariance in steady state, is a constant, there you have it, okay? So this is an example to illustrate the definition, okay? So this is RS at WO. What would be RS I, let's say, at WI minus 1? Well, compute the covariance of this, right? I have to take this thing, this whole thing, multiply by itself and compute expectations conditioned on the past data, right? I think that's what I do in the next example. So in this example, here it is. This is S at omega 0, and this is RS, what I just wrote on the previous slide. They are repeated here. Let's compute the other covariance. That's the covariance for every iteration, not just at omega 0, right? So of course, you have to square both terms and compute. And there is a cross term also, but under expectation, the cross term disappears, right? Because V here, V is uncorrelated with the rest, right? By assumption, okay? Independent of the rest, okay? So when you square, you have the square of the second term, right? Which is simply RS, what we just, and the square of the first term. You see the matrix times W tilde and then the transpose. And because there was a 2, it becomes a 4, conditioned on the past, right? Okay? So if you evaluate this at omega 0, the first term disappears, you get RS, okay? Now, why is it that I'm showing this? Because I want to do some further calculation. I would like to examine this difference here, the difference between this and what it is at omega 0. Right? The value at omega 0, I already know what it is, right? So this quantity minus that, I simply bring this to the left-hand side, right? So this quantity minus that is this term, right? Okay, let's examine the norm of this difference. Okay, I want to show it satisfies the Lipschitz condition. Okay? So here it is. The norm of the difference is simply the norm of that term. Okay, the norm of the, right, if you go back, right, there is an expected value here, okay? So it's the norm of an expected value. This is, of course, upper bounded, right? The norm of the expected value of x, right? This is from Jensen's inequality. You can bound it by the expected value of the norm, right? That's what I'm doing here. Okay, and then the norm of the product of all of these quantities, right, by using the submultiplicative property of norms, you can bound them by the product of the individual norms, right? Did you understand how I arrived at this inequality here? Very good. Okay, now conditioned on F, this W is a constant, so you take it outside the expectation. You will be left with this other expectation, assuming it's a constant, right? That, for example, the data is stationary. We have been assuming that for RU and the mean and so forth. Then you see that you have a sort of a Lipschitz condition, right? A Lipschitz condition between this position omega 0 and, right, and this is W tilde. Because I told you I need to introduce additional assumptions. This is the assumption, that the limit RS exists, right? And that the difference satisfies a Lipschitz condition like that. Okay, this will be part of the assumptions, as you're going to see, okay? And then, of course, if you take expectation here, expectation there, you can get a similar relation involving expectations, fine? This is just an example to illustrate the definition, okay? What about logistic risks? The same thing, these are homework problems. So here I'm just showing you the results, okay? For logistic risk, regularized logistic risk, that's the cost. Okay, if you compute the gradient vector, what's the gradient vector? The gradient vector is rho omega, right? Plus the gradient of this expectation. If you throw away the expectation, you get the approximate gradient, right? So when you subtract the true gradient from the approximate gradient, the rho omega term disappears. You will just get the difference between the expected value and the one without expectation, right? So this is the gradient noise. And then if you evaluate it at omega O, you can show in the notes that this becomes exactly rho of omega 0 minus that, okay? And then you can evaluate the gradient of that, okay? So you can evaluate the gradient of that, RS. This is the definition of RS. You replace omega by omega 0, okay? And then you can show equally using these expressions that I just showed you. This is the RS at omega O, right? And then you have to compute the, what would be RS, what would be this term here? You would have to take this, multiply by its transpose, take expectation. There's some algebra involved here, okay? It's doable, right? It's an assignment and you will be getting solutions, but this is doable, okay? And when you go through that argument, you can show, again, that a Lipschitz type condition holds, but with power here 1. In the previous case, it was 2. Here it is 1. And this is the constant C. Over there, it depended on Ru. Here, it depends on the covariance of the feature data and the third order moment of the feature data, right? But regardless of whether you are doing that case or this case, the important thing is that you have a Lipschitz type condition on the covariance matrix, okay? And you know what the steady state covariance matrix is, okay? Of course, in the logistic case, in the mean square error case, I know exactly what RS is. In the logistic case, I have to compute this expectation to know it, right? So if I tell you the distribution of gamma and H, you may be able to do it either numerically or in closed form, depending on the situation, okay? So, given these conditions, given these examples and these definitions, I told you that I need to introduce 2 additional conditions to be able to proceed with the argument, right? Initially, we assume that the cost function is strongly convex and the Hessian bounded from above and from below. What are the 2 conditions that I need? Okay, I need to ensure, because now remember, I'm using a stochastic gradient algorithm to solve my optimization problem, right? That is introducing gradient noise. Okay, we introduced conditions on the gradient noise, 0 mean. I explained to you last time, this makes perfect sense. You want to use an estimate for the gradient that is unbiased. Okay, and I also told you that I would like the variance to be bounded by a term that depends on W tilde squared and some constant. And that also made sense because I would like the variance of the gradient noise to become smaller as your error vector becomes smaller, right? The better you are performing, you expect the effect of the gradient noise to decrease, right? And this is saying I expect the covariance of this gradient noise to be smooth, okay, to be smooth. If I move a little bit away from where I want to go, right? You don't want the size of this gradient noise, right, as measured by its covariance matrix, to change significantly more than the size of the step. Right? That's what this is saying. You would like the gradient noise to behave well. In what manner? In this manner, right? Okay, if I'm a little bit away from omega 0, that's fine. The gradient noise will have some covariance, right? It will be different, of course, from what you have at omega 0, but in a controlled manner. Okay, and why do I put a gamma here, not just 1? Because you saw 2 examples. For the quadratic case, gamma was 2. For logistic regression, gamma was 1, and there may be other cases. So here I'm assuming that it can satisfy a condition like this for this gamma going up to 4, and you will understand the reason why I introduced 4 later. So this includes quadratic and logistic as special cases, includes other situations as well, but there is a reason why we stop at 4, okay? And the second condition I need to introduce is that the Hessian matrix of my cost function is Lipschitz. Okay, if you remember, when I was talking about the appendix that discusses Lipschitz conditions, I told you that the mean value theorems, we introduced them. The mean value theorem tells you how differences, right, increments in the function or in the gradients of the function relate to integral expressions, right? Integrals of the gradient or integrals of the Hessian. These are general results. But then I told you that in the convex case, I can extract more information from the mean value relations if I assume that the Hessian is Lipschitz, right? That's, if you go back, you will find out, okay, that we did that, and you will see an element of that today. So here I'm assuming a similar condition. That let's assume that the Hessian also, this is essentially saying that your function is smooth enough around the solution. If you are a little bit away from the solution, it doesn't necessarily mean, right, that the Hessian is changing in a drastic way. It's changing in a controlled way, okay? Fine. These I call smoothness conditions. Okay, what they essentially mean intuitively is that your problem is more or less well behaved close to the solution. Okay, it's well behaved close to the solution. Okay, and I gave you examples. In the quadratic case, this is satisfied. In the logistic case, this is satisfied. I showed you this example earlier. Okay, so in all these examples that I'm using, these conditions are satisfied. Okay. Very good. So gamma is 2 for mean square error case, right? Okay, here it is. Of course, here it is. For quadratic case, the Hessian is 0, right? The difference. And for logistic regression, I showed you this result earlier. You see, so this is the constant, and there it is, right? So if you come back, I wanted it to be something times the norm of omega. So it depends on the third order moment of your feature data. And then I just showed you earlier that the Hessian, that the covariances of the gradient noise process satisfy similar conditions, right? So these conditions that I introduced, they are satisfied by problems of interest, and I'm sure they are satisfied by other cases as well, okay? And they have a reason to make sure that your problem is smooth enough, okay? Well behaved near the minimum. Okay. So before I continue, even though these Hessian conditions here, even though these Lipschitz conditions here are required to hold locally an epsilon distance around omega 0, actually they turn out to hold more globally. And if you remember, I showed you a result like this, again, when I was discussing the appendix that discusses Lipschitz conditions. I showed you specifically that this first condition, which requires the Hessian of your cost to be Lipschitz locally, actually is more general than that, and you can say that for any omega 2 and omega 1, you will have a condition like that will hold, okay? I'm not going to prove it again just because it's proven in the appendix, okay? So actually so I can say that because the Hessian is locally Lipschitz, it will be globally Lipschitz with some constant. It will be different from kappa 1, but it doesn't matter, it's a constant, okay? I want to show that something similar holds for the second condition now, okay? Yes?
Probably just said was for convex functions.
Yes, but we are dealing with convex functions here, yes, yeah. The Lipschitz appendix, yes, the appendix on Lipschitz conditions focused on convex functions, okay? Fine. I want to show that something similar holds for the second case, okay? So, in the second case, I'm saying that the gradient, right, is the covariance is Lipschitz within this distance. So let's assume that I took a step larger than epsilon. And I want to show that this difference is bounded by something similar to this. Will not be the same, but similar to this, right? Okay. No, I'm talking, well, if delta omega is any value larger than epsilon, this is essentially telling you that, right, you move as far away as you can, okay? So let's assume, okay, so this is what I just said. Okay, so let's take a step larger than epsilon, fine? Larger than epsilon, okay. And let's show that this remains bounded. Well, from the triangular inequality of norms, this norm is, of course, upper bounded by the sum of norms, right? Let's evaluate each one of these norms now, okay. Okay. Now, so let's evaluate the norm of the first term. Now, covariance matrix is symmetric, right? So the 2 induced norm it's a spectral radius, right? Of course, it's non-negative definite. All eigenvalues are positive. So the spectral radius is obviously upper bounded by the sum of the eigenvalues of the matrix. The trace is the sum of the eigenvalues of the matrix, right? So that's where that first inequality comes from. Okay? Now replace the covariance by its definition. Here it is. Switch the order of the trace and the expectation. You can do that, right? This is not, okay? When you switch, okay, then the trace of the covariance becomes the norm squared, right? The trace of SS transpose, or even here, right? This is a covariance. When you take the trace, it becomes the expected value of S squared, right? But by assumption, this is bounded by beta squared W tilde squared plus sigma S squared, right? Okay, so this is one bound. We bounded the first term. If I replace omega by omega 0, the first term is eliminated, then I bound the second term, which contained omega 0. So I have a bound for the first term, I have a bound for the second term. Add them together. Then you will get this bound plus the other bound, which is sigma S only. So you just have to add a 2 here, right? Okay, so here it is. So the bound is that. So far, so good. Okay, I still have this annoying term. If I did not have this term, then I'm essentially done, right? I would have said that this difference is bounded by some power, right? But I still have this term. Well, let's multiply that term by a number that's larger than 1. Because remember, I took an omega such that this is larger than epsilon. So this number is larger than 1. So I get inequality here still. But now I can group these two terms together, the omega minus omega squared, right? And then this becomes a constant, and then we are back to what I wanted, right? Okay? So what have I shown? So remember, if I am inside, if my delta omega is less than epsilon, this is bounded by some kappa norm of this to the gamma. If I am outside, you are bounded by another kappa delta omega squared, right? Okay. So this difference will be bounded by whichever is the largest value, right? The largest value. You understand? Okay. And the maximum of two numbers is upper bounded by the sum of the two numbers. And this now holds for any omega, right? This now holds for any omega. Okay, but it has, okay, it's the sum of two components, but that's okay. Okay, we'll work with this, fine? Okay, now, so I introduced these two conditions, require smoothness conditions on the cost function on the noise process, and I explained that actually these smoothness conditions hold more globally. If they hold locally, they will hold more globally, okay? Very good. Now, because of that, okay, we can establish the following useful result, which I'm going to use next, okay? But before I get there, I need to remind you of Jensen's inequality because I'm going to use it. Remember Jensen's inequality, right? If f is convex, f at the expected value of a when a is random, this is the stochastic version of Jensen's inequality. That's upper bound. If you switch f and e, right? For convex functions, you get the top. For concave functions, right, you get the, you understand the difference between convex and concave, right? I'm just reminding you because I'm going to use this second inequality here, okay? Now, because of these smoothness conditions I introduced, I can establish this useful lemma, okay? Why is this lemma useful? Let me comment on it. Okay, first, when you study the dynamics of your adaptive algorithms, there is always gradient noise present, right? And when you want to assess the mean-square performance, you square the error recursion, right? And take expectation. So very often you will get terms involving the covariance of the gradient noise. And this lemma is essentially giving you a good approximation for that covariance up to a correction term. Okay? Very good. So what's this result saying? This result is saying that this covariance matrix here, for sufficient I, right, in steady state, okay, remember that what was the definition of RS? It was the covariance at omega 0 in steady state, right? Right? This was the covariance at omega 0 in steady state, right? What this is saying is that if your smoothness conditions are holding, actually as you get closer and closer to the steady state, the covariance is already close to RS, right? Intuitively it makes sense, right? If your covariance matrix is smooth, right? the closer you get to omega 0, the closer the covariances should get to each other, right? So it makes sense to expect a result like this. This is just formalizing it, making it formal. So let's prove that it is this quantity plus a term, and what's the power of this term? It's either 1 or gamma over 2. Remember, gamma is between 0 and 4. So gamma over 2 can be less than 1 still. So that's the smallest, okay? And so this is one way to write it. Another way to write it is, if the covariance is close to Rs, then the trace of that covariance is close to trace of Rs. Okay, it's close to trace of Rs, and B will be of the same size. Right? That's what this second expression is saying. Okay? The trace of the covariance is close to the trace of Rs. Okay? Up to at a difference of that size. That's all. This is what this expression is saying. So let's prove this result before we get to the long-term model. Okay? So remember, I want to show that the covariance itself, not the conditional covariance, which I have here, is the conditional covariance. I have to take expected value of it. But let's continue with this first. Okay? So that's the conditional covariance. I added and subtracted the same term. Nothing changed. Fine? Nothing changed. Okay? Very good. Now, this second term, by definition, it is the covariance at omega I minus 1, right? That's the definition. The last term, by definition, is the covariance at omega 0, right? So nothing changed. I kept that one as it is for the reasons you'll understand, okay? Because technically this is that, but I want to keep it like this. Okay? Okay. So now, take expectation again. If you take expectation, what will happen? This will disappear, right? Okay. Then you will have expectation here. I want to keep this as it is. I don't want to remove the conditional expectation. You will see why. Because when I'm going to take the limit of what is inside here becomes Rs by definition. So that's why I want to keep it as it is, okay? So when you take, here it is, I took expectation. So there it is, I kept the expectation, right? And then you will get the expected value of Rs, okay? Here it is. Right? And then I subtracted that constant from both sides. Nothing changed, right? Because remember, I'm trying to show that this gets close to this. So let's find what the difference is. This is what I'm trying to do. Okay? Okay, so the difference is given by the quantities on the right-hand side. So let's take the norm of that difference, right? Okay? This is just plain algebra. Had I given you this problem as a homework, you would have gone through these arguments, you know. Show that the norm of this is bounded. You would have, because you have to relate it to quantities that you know are bounded, right? That's what I'm doing. Okay. So if I take the norm of the difference, it will be upper bounded by the norm of this plus the norm of this, correct? Okay, you see? Norm of this, norm of this. Okay? Now, norm of unexpected value, I can switch, correct? That's what I did in the second. Just this is Jensen's inequality. Now let's take the limit of both sides. Lim sup of that is upper bounded by the lim sup of this plus lim sup of this. What's the lim sup of this? Well, the limit here is 0 because the limit of this is Rs. This first term, that's why I kept it like this, so that you can recognize that this limit here is Rs. Right? So you'll find that the limit sup of this is upper bounded by the lim sup of this, but this we know is bounded, right? Okay? So here it is. So the lim sup of this difference is upper bounded by the lim sup of that, right? Okay? But now, I told you that this is bounded because, right? Here it is, you see? This quantity here, I just showed you that it is bounded by the sum of two terms, right? Didn't I show you that? By the sum of two terms. Are you following so far? Okay. Now, let's continue. Okay. You already know that the lim sup of this term under expectation is of the order of mu. That's what we proved last time, right? Order of mu. So this term here will contribute order of mu. What about this term here to the power gamma? I know to the power 4. That's O of mu squared, but not to the power gamma. So I transform it to power 4, gamma to the 4. Fine. And now I'm going to use Jensen's inequality. Why? Because here, you see what you have. So I'm going to apply Jensen's inequality to a function that looks like this, x to the gamma over 4. And remember, gamma assumes values in the interval 0, 4. Okay? This function, x gamma to the 4, in that interval, it is convex. It will look like this. At 0, it is 0. It's, sorry, not convex. It's a concave function. Okay? It's a concave function going up like this. Okay? Now, if it's a concave function, what did Jensen's inequality say? F at the expected value of x, sorry, of a, let's say of a, is larger than or equal expected value of f of a, right? Okay? So let's look here, okay? So here you have the expected value of the function, and this is a, correct? Expected value, so you have the right-hand side of the function of a. A is the fourth norm of W tilde. So it's upper bounded by the function applied to the expected value. See, the function applied to the expected value. And this one I know is O mu squared. So this with that will give you O mu to the gamma over 2 from here, and O mu from there, right? Right? And so that's why the right-hand side will give you, okay, so I'm going to write it gamma prime over 2, and I define gamma prime to be the minimum of gamma and 2. Okay. Anyway, so this will be, let me write it more slowly, O mu to the minimum of 1 and gamma over 2. Because you see, I don't know which term dominates, because gamma is between 0 and 4, right? Let's assume gamma is larger than 2. Which term dominates? Because this is mu, this will be a higher power of mu. This will be dominant. If gamma is between 0 and 2, this is dominant. Right? So that's why it's the minimum, either of this or that. Now, I wrote it as gamma prime over 2 because I defined gamma prime to be the minimum of gamma and 2. Okay, so rather than using this, I'm using double that size. Okay? But the important thing is, we concluded that this is exactly what I was looking for, right? That this covariance is indeed close to this by how much? Mu to a power of mu, and I know what this power is, right? This was, okay, the statement of the lemma, okay? Of course, if the norm is bounded, then the trace, right? Then the trace is bounded, right? Because trace is bounded by any norm. You can show that, okay? Okay, so the trace is bounded, and then you get the other result, right? Because if the lim sup of this difference is some power of mu, then this tells you that this quantity here is within trace of Rs plus or minus that quantity, right? Okay, so we established the lemma, right? Fine so far? Okay. I'm going to use these results. So far, I'm just establishing results. I'll put them together for you, okay, once I get to the last part. Okay, let's move on. Now, last time I established that this goes to a region of size mu, right? And that the fourth power goes to mu squared. What about the first power? I mean, the first order moment. I explained to you that because of this relation for any real variable, because the expected value of a squared is upper bounded by that, you can conclude 36, right? That the expected value of the first order magnitude, right, is mu to the 1/2. But then I told you this is a worse bound than O mu. For mu small, this is right. So I wanted something tighter. And this is what the next lemma is showing. That, okay, that I can bound this quantity here, the lim sup of this quantity where the norm, it is the norm of the mean, I'm going to show that the lim sup of that is O mu, which is a tighter bound than this, right? Okay, now in the process of showing this result, I'll start introducing the long-term model. I'm going to get to the long-term model. So, remember, what is my gradient algorithm? Gradient descent algorithm. This is the gradient descent algorithm, right? Right? Okay. Now, I can replace the approximate gradient by the true gradient plus the gradient noise, right? This is what we can do. And then I can use the mean value theorem to replace the gradient of J at omega minus 1 by some integral expression involving the Hessian of J, right? Remember? That's exactly here. That's exactly what the Hessian times, of course, W tilde I minus 1. Right? This is what we did last time when we derived the error recursion for the stochastic gradient algorithm. I replaced that second term, which involves the gradient vector, by an H times W tilde, which I grouped with the first W tilde, right? And then the gradient noise is here. So remember this gradient error recursion. It's very important. It will come up time and again, both in the single agent case and in the network case, we will have the equivalent of this, okay? So this is how the error evolves over time, okay? And we used this recursion last time to show that the second moment and fourth moment of the error are bounded, right? And H depends on the Hessian. H is a random matrix, okay? Now, it's difficult in general to work with this recursion to obtain performance results. You can work with it to obtain stability results, but performance expressions, it's more challenging because H changes with time and is random. Okay, so one way to go around this is the following, right? I know that there is a constant Hessian, right? A constant Hessian, which is the gradient, which is the Hessian evaluated at omega 0. Let's define H to be that. This is a constant matrix, right? The Hessian at the optimal solution, okay? So the difference, how far this is from that value, I'm going to call it H tilde. Just like I call omega tilde is the difference of omega from omega 0, let's call H tilde to be the difference from H to H, right? Okay. Because of that, if I now replace this quantity here by, you see, so the boldface H, I can replace it by H minus H tilde, right? Here. Then this matrix becomes a constant matrix, I minus mu times the constant H. And then you will get a term H tilde W tilde, which is added, correct? Okay, so here it is. I get this recursion, and the term with H tilde W tilde that's added, it is there, right? I did not change anything. Okay. All I did, I changed the dynamics here to a constant matrix, and that error, I put it into a vector C, right? Into a vector C. I'm going to show you that the size of this vector C is small, okay? Small. And later, when I introduce the long-term model, this is what the long-term model will be. I'm going to throw away this. When you throw away this, you're going to be left with a system that's driven by a constant dynamics. And then I'm going to show you actually that the performance of the system is very close to the performance of the actual system, and I will quantify that difference. And for that reason, when we study performance, we focus on this case rather than on the original case. Okay? But let me first show you that this is a small. Okay? Here it is. What is the norm of this vector? The norm of this vector is, of course, upper bounded by the norm, the product of the norms. And then here I replaced, remember, the norm of H tilde. What is H tilde? It is the difference between H and the boldface H. This is the boldface H. And this is the original H. Right? Put them under the integral. Norm of the integral is upper bounded by the integral of the norm. Right? I just did two steps in one step there. Well, this is where I use the smoothness of the Hessian. I assume that the Hessian is smooth. So this norm is bounded by what? By some constant times the difference. The difference is T omega tilde, right? Well, if you integrate this over time, you will get 1/2, and then this W tilde will get squared here, right? So you see that the norm of this vector C, this perturbation away from the original model, its size is of the size of the squared norm of the error vector. And we know that under expectation, the limb sup of this is of the order of mu. So the limb sup of this is of the order of mu. So this vector in steady state is of that size, okay? So if I throw it, I'm throwing away a quantity of that size, okay? I'm not throwing it away yet, but I'm just showing you, I'm preparing you for what will be coming next, okay? You all understand this? Okay. I will be using this later, okay? Very good. So now I can go back to my previous statement that I would like to show that this error quantity, this first order moment, is actually of the order of mu. The proof of that is not difficult, very simple. Okay, so you go back to the recursion, right? Remember the recursion was W tilde I minus mu constant h, W tilde I minus 1, minus mu, the gradient vector, right, plus mu, this perturbation vector, right? Now take expectation of both sides. The conditional expectation of both sides, this term under expectation is 0 mean. So you get, and then conditioned on f, right? So this is a constant, and this depends on W tilde, it's a constant. So that's what you have, right? Take expectation again, you end up with this. Now take the limb sup of both sides, okay, or before the limb sup, let's take the norm, compute the norm here. It's upper bounded by this norm, that norm, right? Okay, now take the limb sup, or, okay. Sorry, again, before that, the norm of I minus mu h, because this is a symmetric matrix, this is rho of I minus mu h, right? And for mu very small, this is 1 minus mu lambda min of h, right? When mu is very small, right? Okay, so here it is. So you get that this norm is upper bounded by 1 minus lambda min of h, that norm, plus that. And now take the limb sup. You can group these two terms together. So in the denominator you get this times the limb sup of that. So you see that in the denominator you have a term of the order of mu. In the numerator you have mu here and mu here. So you have something of the order of mu squared. When you divide them you get what I stated. Right? So this completes the proof that actually your algorithm is stable from these three perspectives, and I give you the bound, okay? Of course, we already knew that the expected value of the norm is bounded, but I wanted to get this tighter bound, and this is the tighter bound, right? Okay? I think by now you are getting used to these arguments, okay? They always involve writing down the error recursion, right? Computing norms of both sides and bounding the norms that you get, right? Bounding the norms of what you get, and one useful element of these arguments, if you go back and always repeat them, this first term we always often write it in the form 1 minus something, so that it is less than 1, okay? And if you go back and revisit the arguments, you will see that this is a theme that runs through the derivations. Okay? So now we are ready to introduce the long-term model, okay? I already showed that the limb sup of this perturbation vector is, right? So in steady state, this enters a region of that size, right? If it enters a region of that size, you can argue with high probability that it will be of the norm itself will be of that size, okay? So that's why I can exclude it. But I'm not going to just exclude it. I'm going to exclude it and then quantify exactly how much I lose by doing that, okay? So I want to argue that actually this norm is of that order, not just the mean, but I can say that the norm is of that order with high probability, okay? So one way to argue that is to use Markov's inequality. What is Markov's inequality? If you have a non-negative random variable, u, then the probability that u is larger than epsilon, or zeta, or whatever you call this symbol, or c, right? Okay, is upper bounded by the mean of u divided by zeta, right? This is Markov's inequality, and I'm not proving it. You can prove it. Okay, it's not difficult. Okay, so let's see. So now let's choose a circle of radius some multiple of mu. Okay, so this circle has radius n, mu, where m is some integer. So what's the probability that the norm of C is within that circle? Well, that's 1 minus the probability that the norm of C is outside the circle. This is a non-negative random variable, so I can use now Markov's inequality. So it is the mean of that divided by RC. But the mean of that is of the order of mu, divided by RC, which is n mu. So you see that this term here will be of the order of 1 over n, right? And I am free to choose n. You can choose n as large as you wish to make this probability, right, as close to 1 as you wish, right? So that's what it means with high probability. So I showed that, you see, once you choose your n, fix n, then you can make your mu as small as you wish, so that the probability that the norm of C is of the order of mu is indeed very close to 1, okay? Anyway, this argument is actually unnecessary for what comes next, but I just wanted to convince you that it's not just the expected value of the norm of C that's of the order of mu. The norm of C itself is of the order of mu with high probability, okay? So now let's go. What is the long-term model? I already introduced the long-term model to you. The long-term model, I'm going to throw away C, because C is of the order of mu, and it's multiplied by mu, so that term is of the order of mu squared. That's driving, okay? Okay. With C, it's exact evolution. Without C, it is a model, right? And this model holds in steady state for I very large, because the bounds on C that I derived, they hold in steady state. To show that C is of the order of mu, I had to use the lim sup bound on the weight arrow vector. So this is long-term model. That's why it's long-term, okay? As for very large values of I. Okay. So now, actually, I'm going to change the notation and put a prime here and a prime there, because the evolution of this system is different from the evolution of the original system, right? Just to distinguish between them, I call the state of this W prime, but I'm not putting a W prime here, because I'm assuming that the long-term model is being driven by the same gradient noise as the original model. This is just, this is just a first-order state space recursion, right? This is just a first-order recursion, driven by an input signal. I'm just saying the input signal here and the input signal there are the same, okay? This signal came from that implementation because it's the gradient noise evaluated at the omega from the original implementation. But this is a signal. So I assume that that same signal is exciting both systems, okay? Both systems. So if I start both systems from the same initial condition, the one with a boldface H and the one with a constant H, if I start them from the same initial condition, and since they are using the same S's, then the respective W tildes, the W tilde there and the W tilde prime here, will both be elements of the same space, right? So W tilde at time I and W tilde prime at time I, they will belong to this space, because they will be linear combinations, right, of all previous W's, right, that belong to this space. This is just a side remark. It might be important for you to know, okay? So here it is, okay? This is my long-term model. Very good. Now, before I show you what I would like to know, remember, the original model had a boldface H here. I would like to know how close this difference, how small this difference is, right? So that you know how close the state vectors are to each other. I'm going to show this later, okay? For now, before I get there, Remember that for the original stochastic gradient algorithm, I showed that its weight error vector is stable from the second moment perspective, from the fourth moment perspective, from the first order moment perspective, right? Similar things hold for this. Let me show that quickly because the arguments for this is much simpler. Because, of course, if I want to approximate a model by another model, if the original model is stable, you better have, right? You better use a model that's also stable, right? So I just want to confirm that this is the case so that you are convinced, okay? So let's show that. Okay, these are just remarks that I already made. Okay, I can skip this part here. So let's show that. So let's show that the long-term model is also stable from the mean square error sense, right? We established the same thing for the original model, right? Let's show that the same thing holds for the long-term model, okay? That it is stable. Let's prove this result before I show you how close they are to each other, okay? So here it is. Remember, W tilde prime is now a constant, right? W tilde I minus 1 prime plus mu s. Again, it's always the same argument. Let's square both sides and take expectations, right? So here it is. If you square both sides, I squared the first term, I squared the second term, the cross term disappears under expectation. That's why you don't see it. Okay, take expectation again, you remove the conditioning, right? It's always the same argument. And expectation here. Well, I can bound this first term here, which is what you have on the next slide, okay? You see, the norm of I minus mu h squared, we already know from previous arguments that it's bounded by this quantity, okay? And you also know from previous arguments that this is bounded by 1 minus mu, okay? This is not difficult. It's easy to show that this is upper bounded, but just subtract and you will see that, okay? Remember, this is 1 here, this is 2 here, okay? I mean, under this condition, okay? So now if you go back, then this variance, okay? So this norm here squared goes out, right? This norm squared goes out, here it is, okay? And then, remember that the norm of the noise, the variance of the noise is bounded, here it is, right? So you get recursion 60. What's special about the inequality 60? You have a recursion with a coefficient here that's less than 1, but you have W tilde in it as well. But that's not a problem, you know, the argument now follows directly. If I take the lim sup of both sides, if I group this term with that term, right? On the left, I will get mu times the lim sup, right? Of what I want will be upper bounded by mu squared, beta squared mu, because I know that this is mu, plus mu squared sigma s squared. And then you divide by this, right? If you divide by this, what do you get on the right-hand side? You get mu, right? Because that dominates the mu squared. Because mu squared over mu and mu cubed over mu, right? You get mu, which is what the result is, right? So the long-term model is stable, right, in this sense. Okay, the second order moment is stable. And then it has this additional property which is useful. The mean error is 0. Okay, the limit of the mean error is 0. For the original model we showed instead this, that the mean error enters a region of bound mu, right? Here, the long term is 0 mean. The mean error is asymptotically 0 mean. Very easy to prove. Go back to the recursion, right? W tilde prime, I minus mu h, W tilde I minus 1 prime, plus mu s. Now take the mean of both sides. This will disappear, right? And then you will get the constant matrix times that mean. So you see, having the constant matrix facilitates these arguments. You see, the proofs for the second order stability and the asymptotic unbiased, the asymptotic convergence of this mean error vector is very simple for the long-term model, okay, because this matrix is constant. So if mu is very small, this matrix is stable and it goes to 0, right? Very good. So now comes the main element of this lecture, okay? The first recursion on this slide tells you how the weight error vector evolves over time. For the regular stochastic gradient algorithm, it has a random matrix H here, which usually, and it depends on omega tilde. Actually, this is a highly nonlinear recursion. Okay. The second system is driven by a constant matrix. This is just the Hessian of your cost at omega 0, right? Driven by some input signal, right? It's not dependent on the state. This is a very regular, right, first order recursion. And I just showed that for this recursion, the mean of this is 0 in steady state, so it's asymptotically 0 mean. And I showed that the second order moment of this also enters a region of order mu, right? Okay? Because the gradient noise is bounded, right? So now what I would like to know is, so these are two systems evolving over time. How close does this stay to that? If they are close enough, then in the next lecture, and they are, otherwise there will be no next lecture, right? And they are, okay, so if they are close to each other, then I'm going to use this system next time to evaluate the size of this second order moment, not just O mu, I'll tell you exactly the size. And then because I know how far it is from this, I can use that error to improve that expression and make it more accurate, right? This will be the argument next time. So this is what I'm going to show now, okay? Here I'm just reminding you that we introduced these fourth order conditions, these conditions on the fourth order moment of the gradient noise. I'm just reminding you of the conditions. I mentioned the second order conditions before. I mentioned the fourth order conditions here because we will need them. Okay, we will need them here. It was because of these conditions that the fourth order moment under expectation enters the region of order mu squared, right? Because I'm going to need that here. Okay, so this is what I'm going to show. Okay, this is the main result that I'm going to show. Okay. So I'm going to show, okay, that the state vectors of both systems, the distance between them is of the order of mu squared, which is very small. If mu is small, mu squared is even smaller, right? Okay, so these two systems in steady state, their state vectors are very close to each other. And I'm going to show that the mean square error that we are interested in is close to the mean square error of this long-term model. The difference is also a higher order power of mu. And even if you compute a weighted norm of W tilde, let's say the Hessian matrix here, the same thing happens. Why do we need this third expression? I'll explain it next time. Okay, we needed to compute another performance metric besides this one. Okay. So what I will do next time, I'm going to give you an expression for this, corrected by this, and then tell you this is the expression for what we want, right? So let's establish these results. Okay, fine. This is what I want to show, okay? The argument, again, is not difficult. If I can give this to you as a homework problem and you will be able to do it, given everything you know so far, okay? Okay, here I'm just restating the result in a more colorful way, right? That's all, okay? This is less colorful. Which one do you like? The colorful? Okay. Maybe I should ask him to make all my slides colorful, right? Okay, so it takes time to do that, you know? But anyway. Proof. Well, if I want to show that one is close to the other, what do you do, right? Subtract the two equations and let's evaluate that difference. if you subtract these two equations, go back, subtract them, right? So this minus that, so this will cancel, right? You will get this minus that. And remember that the boldface H is H minus H tilde, right? So I can replace this by H minus H tilde and subtract, and I can group some terms, right? So this is simple algebra. If you subtract them, this is what you get. Let's go back. This is what you get if you subtract them, okay? And that term that involves H tilde will bring back the C, which we already know in steady state it's bounded by, right, O of mu. Fine? Very good. So technically the norm of this is upper bounded by the sum of the norms, right? Okay? So before I get there, I already know what the norm of this is, right? The norm of that, because remember the Hessian matrix is bounded from below and above by mu and delta, so we have this bound, okay? Which I just explained to you, it's upper bounded by 1 minus mu with 1 here and 2 there, right? Now, this is a useful trick here in this argument, and you will see why very soon, okay? I can add something positive, and the quantity that I added is such that it allows me to rewrite this as a square quantity, and you will see why, okay? Very soon, okay? So sometimes you are going to see this in several of the arguments. Choosing the right upper bound is critical. You know, choosing the right form for the upper bound is critical, okay? And so in this particular case, this will be more useful than this, okay? It will become even clearer later when we study networks, okay? So now, let's do the following. This function, of course, is convex, right? X squared is convex, okay? And let T denote this quantity here, mu lambda over 2. You see, this quantity here, let's call it T. Look what I'm going to do now, okay? And of course, T is between 0 and 1 if mu is very small, because that's usually the case. So I'm going to use T and 1 minus T as convex combination coefficients. So look at this argument here now, okay? So I'm squaring both sides, right? So I squared the right-hand side. Right, there it is. I squared the right-hand side. You see, before we used to square and take expectations, correct? You might say, why are you doing a different argument now? Because I know I can tell from your faces, okay? Before, I had an error recursion. I used to square, and then I would tell you, take expectations, the cross terms disappear. But now, if I square and try to do the same thing, you see, I can square. But then you see, the cross term involves C with these quantities, and C has W tilde in it, right? So it's not, this cross term is there. You have to live with it, right? Okay, so I'm using a different argument now, which will help address this difficulty, okay? You understand why I'm using a different argument? Because otherwise I will have this cross term. So the different argument is, look, I want to square the right-hand side, okay, and I want to avoid the cross terms, right? This is a nice trick. Think of Jensen's inequality. Look how, okay? Look what I did. I multiplied by 1 minus T divided by 1 minus T. Did I change anything? No. T and 1 over T. Did I change anything? No. Fine. But now you can think of 1 minus T and T as two convex combination coefficients, right? And the norm of x squared is a convex function, right? Okay, so a convex function, so here, 1 minus T times 1, right? Sorry, it will be 1 minus T times this whole thing squared. I just did 2 steps in one. That whole thing squared is, of course, upper bounded by the product squared. And then T times that whole thing squared. You see? No cross terms, right? Okay, this is good so far. Now, of course, the square of this, you get 1 over minus T squared, so you are left with only 1 over 1 minus T. The norm of this squared, we said, is this, right? And here you get 1 over t. Now you see, you appreciate why I express the norm of I minus mu h squared as a complete square. Because t is mu over 2. So this cancels that, and you will remain with one coefficient, 1 minus something. Right? So you get that coefficient, right? Had you had only 1 minus mu nu here, without the square, right, then it would be more difficult for you to get the coefficient here, to rewrite this in a form that has 1 minus something. You understand it? Did you understand why this was useful? Okay. So this is that. So now, and remember, on the left-hand side, I will get something like this, right? If you put them together, everything together, right? So now, if you take the lim sup of this, you can group this term with that term, right? 1 minus 1 minus, you'll get mu nu over 2, right? So I'm going to divide by it, correct? On this side, what do you have? Let's look. On this side, you have mu squared over mu nu. So on this side, you have 2 nu divided by nu, right? Times norm of c squared. And that one is what? Nu squared. Because we showed the expected value of the norm of c is of the order of mu. And then you're going to divide by nu over 2. The important thing is that you have the mu cubed in the numerator, mu in the denominator, so this will give you the mu squared that we claimed, right? Going back to this colorful slide, we claimed the mu squared, right? You see how I got it? Anyway, you have to see it once at least so that you get an idea of these types of arguments, okay? And we'll be using these types of arguments in several places. When we have correlated terms like this is a useful thing to remember, okay? Okay. Now, so I already showed you this, right? From here I concluded the first equation. Let's go now to the second result. I'm not only interested in showing that this difference in steady state is of the order of mu squared, which I already showed. I'm also interested in showing that the lim sup of this is close to the lim sup of the similar term for the original system plus a small error. Okay, so here it is. So this quantity, I add and subtract W tilde. Nothing changed, right? Okay. Now you can expand it, right? Here I just expanded it. If you expand, you will get this square plus this square plus the cross terms, right? Plus and remember, everything is positive here because it's norm squared. The cross term, and you'll get 2 of them. Fine? Okay. And now this is up here. I use Cauchy-Schwarz, right? This is an inner product between 2 vectors. You can bound them by the norms, squared, square root. Okay? Why I'm doing this? Why? Okay? Can you tell me why? Yes.
Why did you put the absolute value in the third term?
Sorry?
In the cross term?
No, just to ensure that it is positive, because this result is positive, right? It's the expected value of a norm is squared. If you just put in a product as it is, you are not guaranteed to have. Okay? So now, using Cauchy-Schwarz, this is bounded by that. Why I'm doing this? I'm expressing everything in terms of squared norms because I have bounds on all of these squared norms now, right? Under lim sup. So remember, I want to know how far the lim sup of this is from the lim sup of that, right? Okay, well, I already know this quantity in steady state is mu squared. This quantity in steady state is mu. And this quantity here in steady state, mu squared. So you get square root of mu cubed. So this second term gives you mu 3/2. This first term gives you mu to the 1/2. Which term dominates? This one. So you see the lim sup of this is far away from the lim sup of that by this much. Right? You get it? Okay? By this much. And then similarly for the last part of the lemma, which involved a weighted, okay, I wanted to know the difference between weighted norms. You can repeat the argument by using weighted inner products. Okay, so this is a weighted inner product between two vectors A and B. So this is the extension of the Cauchy-Schwarz inequality. The one that I meant, of course, this is under expectation, right? Under expectation. You understand that first result there, right? This is not for standard vectors, right? This is for random quantities, right? You see, you probably know this for deterministic vectors. For deterministic vectors, you know this, correct? Right? So this holds. But now A and B are random vectors. For random vectors, you have this. Of course, you can write this, but you can also write this. Okay? Because the expected value of two random variables, you can treat it as a definition of an inner product. Okay? You can think of it as a definition of an inner product. Okay? And, right? So the norm of A squared there in this definition of inner product, right? Of course, you can make this very formal, right? You can make it more formal. Sorry? No. Yeah, no. For any, this is an upper bound, okay? An upper bound, okay? A and B are any random vectors, okay? And then this is the extension of it when you have a weighted inner product. A weighted inner product, what will happen? You bound, and then here you will have the spectral radius squared of H. H is a symmetric matrix here, non-negative definite or positive definite, right? Well, you just apply that property to A, HB. A, HB. Okay? This is a weighted norm of B. And from Rayleigh-Ritz, right? This is upper bounded by rho squared of H times that, right? And that's how you get this other result here, okay? And all these terms, again, will lead that the difference in steady state will be of this size, okay? Good. Okay. So you understand what we did today? Okay, just to give you a 1 minute brief, right? We studied the same stochastic gradient algorithm from last time, where you use the approximate gradient, right? So last time, I showed that if you use the approximate gradient, the algorithm remains stable. In what sense? If you compute the weight arrow vector W tilde, its second order moment, norm squared under expectation, or fourth order moment, norm to the 4 under expectation, right? I showed you that these limits, they enter regions of the size of O mu or O mu squared. So that proved that the algorithm remains stable, of course, under certain conditions on the gradient noise process, right? That the variance, the second order moment of the noise or this and the fourth order moment of the noise are bounded. Fine? Okay. What I did today, okay, I motivated a long-term model. I told you that I'm not only interested in knowing that the expected value of W tilde squared enters a region of size O mu. I would like to know more precisely what is that radius, right? I would like to know more precisely, right? What is that size, okay? To do that, I said, and you are going to see more of this in the next lecture, it will be easier if I work with a long-term model. Why? Because if you write down the recursion for the original gradient, stochastic gradient algorithm, you get a recursion that involves a boldface H, which is random and time variant, right? This recursion was very useful for us to ensure stability, to study stability properties. That's what we did last time. We simply worked with that recursion and we bounded H and so forth. But now to come up with more precise expressions for what the MSD, mean square deviation, that's what we are going to refer to that quantity in steady state, to come up with expressions for that, more accurate expressions for that, it will be easier for us, and you will understand this better next time, it will be easier for us to work with a long-term model which replaces the bold phase h by a constant h. The noise process is still the same. Okay? Then I showed today that this model is still stable. Its second order moment is bounded. Lim sup is of the order of mu. The expected value of W tilde goes to 0, so it's asymptotically 0 mean. And then I showed you that actually this trajectory in steady state evolves close to that trajectory, and I quantified exactly the difference. So if in the next lecture I come and I tell you I find an expression, in the next lecture if I find an expression for this quantity here in steady state, I tell you this is the expression, then I know that if I correct it by 3/2, I will get an expression, right, for the original system, right? So I'm going to be following arguments like this, right? And remember, we derived these results by introducing two conditions, two smoothness conditions. The Hessian of the cost function is Lipschitz, and the gradient covariance matrix also satisfies the Lipschitz type condition, right? With a certain factor gamma there, which is useful, okay? Fine. So do you have any questions before I conclude? Okay, very good. Thank you then.